Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the sampling distribution of the sample mean x bar. And here is one of the important results related to the idea of sampling distribution. Well, if x bar is the mean of a random sample of size n from a normal population with mean mu and variance sigma squared, then the sampling distribution of x bar is also a normal distribution with mean mu and variance given by this one, sigma squared over n. So if I were to translate this whole long statement into a mathematical representation, it will simply look like this. So here I will have a distribution of x. X is a normal distribution, has a normal distribution. According to this statement here, we sample the data from normal population with mean mu and variance sigma squared. So the original population has a normal distribution with mean mu and sigma squared. And then imagine you take a random sample of size n. Therefore, what is the distribution of x bar? So the distribution of x bar will also be normal with the same value of mean, which is mu. So it has the same value as the original x. And the variance, however, is going to be slightly different. The variance here is going to take into account that you sample a certain number of size. So here variance is going to be sigma squared over n. So notice the difference between this one here and this one. So in one glance, you can see that the distribution for x here has a larger spread of data because the variance here is bigger than this one. So here the variance is sigma squared over some value n. So in reality, this here will give a smaller spread of data. Okay. What is the graphical meaning of the above statement? Well, this is the idea. Well, you can see, for example, here is our random variable x. You can see the spread of data here is the largest compared to this one and this one, because these two here is the distribution for x bar. So x bar, the variance for x bar is smaller than the variance for x. X is sigma squared, this one is sigma squared over some other value. So therefore, variance of this is smaller. You can see this one is smaller than the first one. This one is also smaller than the first one right here. Also, if you take a sample size that is larger, then the variance is going to be smaller for that distribution. So for example, this is the sampling distribution when you consider taking a random sample of size n equals to 5, and therefore you can see this is the spread of the results, which is larger than this one. Okay, because this one is the sampling distribution of x bar with n equals to 30. Now it makes sense because imagine you have some value, sigma squared over 5, and you compare it with another value where you have the same sigma squared, but you divide that with 30. Of course, the result here is going to be smaller. So when it is smaller, it reflects in the spread of the results here. You can see that a lot of our results will cluster tightly around the value of mu. Okay, and in the original distribution, the mean of x is at position mu, so here is the mean at mu. And similarly for x bar, the center position, the mean of x bar is also at position mu. So mu here doesn't change. What changes is just the spread of the distribution. Okay. Now what is the implication of this result given here? Okay, so here is the result. We have, let's say our original distribution has n. It is a normal distribution with mean mu and sigma squared. Therefore, x bar will be automatically normal as well with mean mu and sigma squared over n. This is the variance. Well, by having this, we can easily make probability questions. We can easily answer the probability questions about x bar. For example, you can give an answer to what's the probability that x bar less than some value, or what's the probability of x bar greater than some value, or between two values. So you can answer these probability questions about x bar. Now remember what I've told you about solving probability questions related to a normal random variable. For example, x here is a normal random variable. So if you want to convert from x to z, okay, because we need to convert it to a standard normal. So z here is the standard normal in order to easily calculate the probability of it, because we already have the standard normal distribution table, right? So what you have to do is you can apply this formula. The formula here is x minus mu over sigma. So x here is the value of normal random variable. Mu here is this mu related to mean of x. And sigma here is the standard deviation of x, which is this guy here. Square root of sigma squared is sigma. Now, the same thing can be done for this guy here, because x bar also has a normal distribution. That means x bar is a normal random variable. So if I want to know what's the probability of x bar less than a or greater than b, I can apply the same process of converting x bar to a standard normal random variable, to the z-score, okay? Therefore, for this one here, it's going to be z is equal to x bar, because x bar here is our normal random variable now, minus what is the mean of x bar. The mean of x bar is the same thing, which is mu. What is the standard deviation of x bar? Standard deviation of x bar is square root of this one. Okay, so square root of sigma squared over n, which can then be simplified as such. Okay, so we are able to convert x bar here into z-score using this formula, and we will be able to find the probability associated with that by just referring to the standard normal distribution table. You will see example of this later on, okay? Now let's move on to the next idea related to the sampling distribution, which is the law of large numbers. In simple words, it tells you the behavior of the sample mean. It tells you how sample mean behaves when the sample size gets larger and larger. So when n gets bigger and bigger, you will see that the value of sample mean will get closer and closer to the population mean. So population mean here is mu, okay? So in simple words, as the sample size grows, the mean here will get closer to the average of the whole population, which means here is mu. The average of population is mu, okay? And this is illustrated by the graph here. For example, if you roll a dice and you observe the mean of the result. For example, you can see from the results here, when the sample size is between maybe 0 to 100, you can see the results here fluctuate quite far from the theoretical mean. So the blue line here is the theoretical mean. Theoretical mean is referring to the value of mu. What's the population mean, okay? So the population mean here is 3.5, and you can see that when the sample size is smaller compared to this one here. Well, for this one here, you can see, for example, between 600 to 800, the result here given by the green line gets really close to the theoretical mean 3.5. So that is the idea of law of large numbers in simple words. However, the law of large numbers has a lengthy discussion actually. They are related to, for example, weak law of large numbers, and there are also strong law of large numbers, and you have to, like, if you're interested in this, you may want to go on and do a bit more reading related to this one. And this is one of the quite well-known idea on the law of large numbers. This is related to the Chebyshev's inequality, where you have, for example, any positive constant c, the probability that x bar will take on value between mu minus c and mu plus c is at least this result. And when n approaches infinity, the probability is approaching 1. So what it really means is, if I'm translating the long statement here into some simple mathematical statement, well, it means that probability that x bar here will take on value between mu minus c and mu plus c. That means it's between mu minus c and mu plus c. The probability here is at least, so at least is, it could be greater than or equal to, so it's going to be at least 1 minus sigma squared over n, and this is the constant c squared. Okay, so that is the mathematical representation of this statement given here. And I hope you can see that when n gets bigger and bigger and approaches infinity, this part here is going to disappear. It becomes 0. Yes, therefore the probability that you're looking for this guy here is going to approach 1. So that is the idea really. And if you want to know more about it, you can go on and search for Chebyshev's inequality. Okay, right, let's move on to the idea of central limit theorem. This is the third idea. So this idea of central limit theorem says that doesn't matter what the shape of the original population is. For example, it could be the original population may have the uniform distribution, it may have skewed distribution, it may have an exponential distribution. Doesn't matter what the shape of the population is, but if you take a sample size that is large enough, the distribution of x bar is going to be normal. Okay, the sampling distribution of x bar will be normal or approximately normal. So here is the difference between this case and what you have seen in this case. I can call this is the first case. Case 1 is when the population distribution is normal. Population distribution is normal. Then what is the sampling distribution of x bar? So x bar is automatic going to be normal with mean mu and variance sigma squared over n. Now we might have other sort of population distribution. In this case, doesn't matter what the shape of the population is. It can be uniform, it can be skewed to the right, it can be exponential, doesn't matter. What the distribution is, it doesn't matter what the distribution is. The sampling distribution of x bar, that means our x bar here, is going to be normal, provided that the sample size we take is large. And usually they say that large sample size is when n greater than or equal to 30. Okay, so that's the idea. So this could be the original population distribution. This could be our x. It can have whatever shape. There is a mu. The mean here is mu. and the spread of the graph, the standard deviation is sigma. So if you take a large n, a large sample size, therefore our x bar here is going to look like this. It's going to have a normal distribution. Okay, so this is for x bar, this is x. Our x bar here will look normal like this, where the center point here is at mu, the same value as the original distribution, and the variance or the standard deviation in this case is sigma over square root n. Okay, so maybe I can try and write down the result. So let's say doesn't matter what the population distribution is. Okay, doesn't matter. If n is large, then this is the result that we have. Then x bar, the distribution of x bar, is still going to be normal, or people like to use the word approximately normal, with mean mu, and that variance is sigma squared over n. So the variance is still sigma squared over n. Okay, so the result here is similar to what you have seen for the first case here, but the difference is that in the first case, it doesn't matter what size that you take. It can be small, it can be big, it doesn't matter, because the original population here is normal, so therefore x bar is just going to be normal straight away. But for this one, it is only going to be normal or approximately normal if n is large. So this is the result that you can use. Okay, so here is the result, the important result of central limit theorem. Okay, and so here is example of useful result where you have x1, x2, xn that comes from an infinite population. We don't know what the shape is, so no idea what the shape is. Okay, but we know that it has mean mu and variance sigma squared. Therefore, if you take a large sample, so n is approaching infinity, so that means you have a large number of data, a large sample. Therefore, the result here is going to be standard normal distribution. And the implication is that, well, like I said earlier, we have x is unknown distribution, but we take n, such a large number of n. Therefore, we get this result. We know that x bar is going to have a normal distribution with mean mu and sigma squared over n. So this is the result of x bar. And because of that, we can make probability statement about x bar. What I mean by that is I can ask, what's the probability x bar greater than a? What's the probability x bar less than b, for example? So those are the sort of probability questions that you can ask related to x bar. And in order to answer these probability questions, I've explained to you just now that we need to be able to convert x bar into a standard normal distribution or standard normal random variable or z-score. And to do that, that means I have to use this formula. Z is equal to, what's the normal random variable in this case? The normal random variable is this one. This is x bar. X bar has a normal distribution. What's the mean of x bar? The mean of x bar is this guy, so we're going to minus mu. What's the standard deviation for x bar? Standard deviation for x bar is this one, square root of this one, which is sigma squared over n, square root of that, which can be simplified as this one. Therefore, this is already a standard normal z-score, and you can use the standard normal distribution. So this guy here has a standard normal distribution. Yeah, this is what's given by this statement right here. Okay, right. Let's look at some examples here. Well, let's see that here what we have is we have random variables x1, x2 until xn. They are all independent random sample from an infinite population. We don't know what sort of population they have, what sort of distribution, but it doesn't matter because it shows that they have like taking or considering a large sample. And we are going to show that expected value of x bar is mu and variance x bar is given by this one. We're going to show that this result is true. Expected value of x bar is mu. This is expected value of x bar, and this is variance of x bar. Sigma square over n here is the variance of x bar. Okay. So what is expected value of x bar? Expected value of x bar is the expected value of x1 plus x2 plus x3, and you go on adding up until the last random variable, and you're going to divide that with n. So that is x bar. You have done this so many times before in chapter 4 related to mathematical expectation, right? Now 1 over n here is a constant. We can take it out, so put it outside. Therefore here we have expected value of x1, separate them accordingly, plus expected value of x2 plus blah 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 expected value of xn. And it says here that each x1, x2, xn, they are independent and they come from the same population. That population says the mean is mu, so we know that for this one here the mean of x1 is mu, this one also the mean is mu, and until the end the mean is mu. So here we have mu plus mu plus mu plus mu n times. Okay, it happens n times, so we can write down this result as 1 over n times mu, because mu here happens n times. You can cancel out n and n, so expected value of x bar is just mu. Okay, so that's the first result that we have. Okay, now let's look at the idea of finding variance of x bar. Okay, I'm going to erase this part. Okay, so next part is to study variance of x bar. I'm just going to replace this with v. Okay, so here we've got variance of x bar is the same thing as this one. X bar is this process, and again 1 over n is a constant, so this is actually looking like this, 1 over n. You can take it out. Okay, you can factor 1 over n out, so here we have x1 plus x2 plus x3. Yeah, I might not show that clearly or explicitly in the first example, but that's the idea, right? When you have this statement here, it is the same thing as putting 1 over n outside, and here we have x1 plus x2, x3 until xn. 1 over n is a constant, so when you take it out from the process of finding variance, don't forget you have to square it. If you don't remember what's going on here, you really need to go back to chapter 4 mathematical expectation and see the videos related to this. Okay, so this one will be multiplied with variance of x1, x2, x3, xn. Okay, next, this is the same thing as 1 over n squared, variance of x1. Now because they are independent, so we don't need to consider covariance. Covariance x1, x2, x1, x3 and so on. We don't need to consider the covariance because they are all independent. So it becomes variance x1 plus variance x2 plus variance x3 until the end. Okay, and this is the same thing as we know all these random variables have the same variance. The variance is given by sigma squared. It comes from the same population. So here we have sigma squared plus sigma squared plus sigma squared, and it happens n times, okay, because we have n random variables. Therefore here the result here can be written as 1 over n squared n times sigma squared. You can cancel out n with the one at the bottom, so you are left with sigma squared over n, and so you are able to prove the result given here. Okay, right, let's look at the example. Okay, so here we have a soft drink vending machine is set so that the amount of drink dispensed is a random variable. So the amount of drink here is a random variable. I'm going to call it x. It has a mean of 200 ml. So this is the mean of x, or expected value of x, ex. Standard deviation is 15. What is the probability that the average amount of dispensed in a random sample of size 36 is at least 204 ml? Now look at this statement here. This is average amount of dispensed. That means average of x. That means you're talking about average, which is sample mean. Okay, x bar, you're talking about x bar. X bar here comes from sample size of 36. This is n. At least 204, that means greater than. At least means greater than or equal to 204. So here the sample size is obviously big enough, 36 greater than 30. You can see that we don't know what's the original population is, the distribution of the population is. We only know that x here is representing the amount of drink dispensed, and we don't know what is the distribution, whether it's uniform, whether it's normal. We have no idea about it, but it doesn't matter. We know other information about x, which is expected value of x is 200 ml. This is actually mu of x. I'm going to write down here mu of x to be more specific. And then we have standard deviation of x, or in other words, variance of x is 15 and you square it. Okay, so that is variance of x. So because the sample size here is bigger than 30, okay, this is 36. Therefore, using the central limit theorem, based on the central limit theorem, we know that our x bar, okay, our x bar is going to be normal with the same mean, which is 200. It's going to be normal, and the result here is going to be the result here looks like this: mu sigma squared over n. This is based from the theory here, so this one, okay, this is a theory, the theorem related to the sampling distribution of the sample mean. Okay, it doesn't matter what the population distribution is. It doesn't matter. As long as the sample size is large, then x bar is also going to be normally distributed. Okay, with this one, mean mu, variance sigma squared over n. So we're just going to use that result really. Okay, so based on this, we know that x bar has a normal distribution. Mean is 200. And variance is going to be 15 squared over 36 is the sample size. So this is the value of variance. And by having this, okay, we can easily answer any probability question related to x bar. So in this question, it is asking you to find the probability that x bar here at least 204 ml. And in order to answer this probability question, I need to convert x bar into a z-score so that I can use the standard normal distribution table in order to find the probability associated to this. So what I need to do is I need to convert that by having x bar minus the mean of it. The mean of it is this one, which is its mean here is 200. Okay, I'm just going to write the formula first. We're going to minus with mu, and then we're going to divide that with the standard deviation. So this is variance. therefore standard deviation is sigma over square root n. Okay, and that is greater than or equal to, well, if you do changes on this part on the left side of the inequality, therefore you have to do similar changes on the right hand side of the inequality. So here we have 204 minus mu over the same thing, and this now will be transformed into a z, which is a standard normal random variable. So here we've got z greater than or equal to, this one is 204 minus 200 over, the standard deviation is going to be 15 over square root of 36. And you will see that for this one, we are looking to find the probability that z greater than or equal to 1.6. We can use the standard normal distribution table. For example, you can use this table. Well, what it means by this, that means if I sketch the area that we are looking for, so this is 0.0, 1.6 maybe somewhere here, and you're looking at this area. You want to find what is this area. Okay, so this is z greater than or equal to 1.6, this area. Well, if you look at this table given here, what it gives you is, it gives you the area from one value to the left. Okay, so this is what I'm looking for. This is at z 1.6. So if I go on and read from the table, 1.6 is here, this is z value. So the answer here is 0.9452. So 0.9452 gives you this area, 0.9452. What I'm looking for is this area to the right. So what we have to do is we are going to write down 1 minus 0.9452. So 0.9452 is this area to the left. What we're looking for is this one. Okay, oops, sorry. So the answer is going to be 0.0548. So that is the probability that the average amount of dispensed is at least 204. Okay, right. If you want, you can try and use this table to get the result. Shall we do it together then? Okay, so if you want to use this table, well, this table gives you the result from the middle point 0 to, for example, 1.6. So if you go and read 1.6 right here, it gives you 0.4452. So this is the result given by this table. Again, what I'm looking for is I'm looking for this area. So how do I find this area? Well, I can find this area if I have 0.5. I take all this part here, 0.5 minus 0.4452. So if I do that, I should be able to get the same answer really. Okay, so 0.4452. It's going to be 0.054480. Okay. Right, I think that's all for now. Thank you very much for watching, and I'll see you in the next video.